Hey guys, Miss Peterson here, and welcome to AP Chemistry Lecture 8-2, all about weak acid and base equilibrium. This is going to feel a lot like our equilibrium unit, okay? This is not that new a concept. It's just taking what we already know and applying it to acids and bases. Okay, so we're going to be talking about Ka values and Kb values, pKs, pKbs, and percent ionization. So, we already learned about strong acids. Now, those are ones that ionize completely. They completely break up and produce all of the H+ ions they can, where a weak acid does not ionize completely. It will get into a weak acid-base equilibrium. And there are two kind of ways that you'll see that represented. Okay, sometimes you'll see it represented with that H2O, showing the hydronium ion, the H3O+. But often we'll show it without that H2O and just show that H+. However, these are equivalent, okay? These have to be equivalent in your brain. You'll see both of them. You'll use both of them. On your equation sheet, it's written in this form. But again, a lot of old textbooks and stuff will still use this form. So I want you guys to be able to recognize both of them. And note, when we do our rice tables or our net ionics, we don't include the liquid water anyways, so it's not going to make a difference in our calculation which version we're using. Okay, but yeah, this H3O+ is called hydronium, and it's what happens when that H+, which we sometimes just call the proton, bonds to a water molecule. Okay, and then we have our A-, that is going to be the conjugate base, aka that deprotonated acid. Yep. So, in thinking about how the strength of an acid compares with its Ka value, well, we know K is the products, which include that H+, over the reactants. And so, since the more H+ ions you have, the stronger the acid. Okay, that means that the higher the Ka value, the stronger the acid. Okay, strong acids will have Ka values on the order of like 10 to the +4, +5, +14. Okay, where weak acids will have Ka values on the order of 10 to the -3, -4, -5. Okay, so and then again, here's just a visual of that. In the strong acids, the HA molecules completely dissociate. So you have all H3O+ and A-, where in the weak acid, only some of them dissociate. So you have some H3O+ and A-, but a lot of the acid stays together. Okay, cool. So how do we use this? Well, a student prepares a 0.1 molar solution of formic acid, a weak acid, measures the pH to be 2.38 at 25 degrees Celsius. Calculate the Ka value for the formic acid. Okay, well, we're going to go ahead and write this out. So the reaction that we're talking about is that formic acid. So we got HCOOH, and it's a weak acid, so it'll break apart into H+, and that COOH-. Okay. We are given the initial concentration of that acid to be 0.10 molar, and then we have the pH. Now, since we know that pH is the negative log of that concentration of H+, in order to undo a log, it's going to be 10 to that value to get the concentration of H+. So the concentration of H+ here will be 10 to the -2.38, which gives us 10 to the -2.38 gives us 4.17 times 10 to the -3 molar. Yep, cool. So that is our concentration of H+ at equilibrium. 4.17 times 10 to the -3. Now, if we're thinking about this as a rice table, we got -x and then +x and +x, because for every one of those that dissolves, it creates 1 and 1. So given that, we know that x is going to be 4.17 times 10 to the negative 3. So our concentration of that one is also 4.17 times 10 to the negative 3. And our concentration here is 0.1 minus 4.17 times 10 to the negative 3, which gives us 9.58 times 10 to the negative 2, or 0.0958 if you're not in scientific notation. Okay. Now, what we're going to do is we're going to plug those values into the Ka expression, which will be the concentration of H plus times that concentration of A minus, aka the COOH minus. Again, just products over reactants, no different than our equilibrium unit. But we can plug in our values. We got 4.17 times 10 to the negative 3 for both those final concentrations or equilibrium concentrations over the 0.0958. And we plug that into our calculator. 4.17 times 10 to the negative 3 squared divided by 0.0958. And we get 1.814, so 1.8 times 10 to the negative 4. We'll go 1.81 times 10 to the negative 4 will be that Ka value for the formic acid. Okay, cool. Okay, cool. Let's try another one. So this one, we're going the other way. We're given a Ka value, and we're asked what's going to be the pH. So I'm still going to go ahead and set up that rice table so we understand what we're looking at here and what we're solving for. Okay. We're looking at the acetic acid, H plus and CH3COO minus. Okay, we are given the Ka value, which will be that concentration of H plus times the CH3COO minus over the concentration of the CH3COOH to start. And we know that's equal to 1.8 times 10 to the negative 5. We're given that initial concentration of 0.30 molar. Okay, none and none, so we know some of that's going to go away. We got X and X, so 0.30 minus X, X, and X. Since the Ka value is on the order of 10 to the negative 5, we know X is going to be really, really small. So we can use that small order one and say this is going to be approximately equal to 0.003. Okay. So now plugging it back into the Ka value, we have X and X, so X squared over 0.30 equals 1.8 times 10 to the negative 5. And we get an X, which is our concentration of H plus. Move that up a little bit. We get an X, which is our concentration of H plus, to be we got 1.8 times 10 to the negative 5 times 0.3, and then we take the square root of that. And we get an X value of 2.32 times 10 to the negative 3 for our concentration of H plus. So if we want to know the pH, pH is the negative log of that concentration of H plus. So we take the negative log of that answer that we just got, and we get 2.63. And that's going to be the pH of our solution. Okay. Does it feel familiar like acids and bases? Okay, cool. Or familiar, it is acids and bases, but does it feel like our equilibrium problems? Good. Okay. One other way that we kind of quantify acids and bases is through their percent ionization. So for percent ionization, it's going to be the concentration of the ionized acid over that original concentration of the acid. And then like all percentages, you times it by 100 to get it in percent form. So if we want to know the percent ionization for a 0.035 molar solution with a pH of 2.34, well, we can use the pH to tell us our concentration of H plus. It will be 10 to the negative 2.43. So 10 to the negative 2.43 gives us an H plus concentration of 3.715, carrying a couple extra sig figs here until we get to the end, times 10 to the negative 3 molar. So that will be the concentration of the ionized HA, because ionized means it'll be H plus and A minus. So we can do that number over the original concentration, 0.035, and then times it by 100%, divided by 0.035, and we get our answer of 10.6%. Okay, cool. Okay, cool. So, another thing we need to talk about, well, a couple other things, but one of them is polyprotic acids. Okay, so a polyprotic acid is just what it sounds like. Poly, many, protic, proton, many protons. So it has more than one H that can be ionized. So if we look, for example, at like, let's look at carbonic acid. It has 2 Ka values because there's 2 H's that can be ionized for it. What that means is this Ka1 is for the reaction of H2CO3 going to form H plus and HCO3 minus. That is going to be your Ka1, that 4.3 times 10 to the negative 7, where the Ka2 comes from the second H being ionized. So that HCO3 minus can be further ionized to H plus and a carbonate ion, CO3 2 minus. And that Ka value is obviously going to be a lot lower. Okay, the Ka1 is always going to be greater than Ka2 because it's the first one that gets removed. So it's going to be removed the most. It's the easiest one to remove. So it'll always be highest. So sometimes they'll ask you about like the concentration of these different ions in solution. So this one would be the one present in lowest concentration, where since this is still a product favored reaction in a solution of carbonic acid, the carbonic acid will still be what's present in the highest concentration. Okay, cool. Okay, cool. So we talked about weak acids. On the flip side of that is our weak bases. So a weak base removes some H plus from water. They'll often have those OH minuses. And then I did want to talk about the strong bases and strong acids. I have a little table down right here. Okay, and unfortunately, these you just gotta memorize. Okay, we gotta memorize the 6 strong acids. And then one trick that I've learned for the bases is that they make a B on the periodic table. So if you go, let me look at this periodic table. Okay, the bases make a B. Well, let me draw. No, but they make a B on the periodic table. So you can kind of see that there, the lithium, sodium, potassium, and then calcium, strontium, barium. Rubidium and cesium would be considered, but they're so volatile, they're not really used that often. Okay. So all other bases are going to be weak bases. And we have that general equation. Because it's stealing the proton from water, you will almost always see it represented with that water, producing that Hb plus and that OH minus. So let's go ahead and look at an example. Okay, this one says to calculate the concentration of OH minus in a 0.15 molar solution of NH3. And we're given the Kb value. Also, we'll do it again in a 0.30 molar solution. If it's twice as concentrated, are we going to have twice the basicity, basicness of it? Let's go ahead and find out. Just like our acid problems, we're going to start with a rice table. Okay. And the reaction that we're looking at is NH3. And it will react with water to produce its conjugate acid, NH4 plus, and leave that OH minus. Again, water is a liquid, so we don't need to worry about it in our rice table. We have our initial concentration of 0.15, and then we know that we'll have X and X. So we got 0.15 minus X, X, and X. And like in our acid problems and 90% of our equilibrium problems, X is going to be pretty small, so we can treat the 0.15 minus X as just 0.15. Setting up our KB expression, this one right here, to be, we got 1.8 times 10 to the negative 5 equals X times X, so we're going to go with X squared over 0.15. So then we get an X, which is our concentration of OH minus, to be, we got 1.8 times 10 to the negative 5 times 0.15, and then we take the square root of it, and we get 1.64 times 10 to the negative 3. Yep. And that's in the 0.15 molar. To do the 0.3 molar, we're not going to have that much different of a calculation. It's just going to be a different initial concentration. So I can set that up using pretty much the same equation. And we get an X, which is our concentration of OH minus, to be 1.8 times 10 to the negative 5 times 0.30. Take the square root of it. And we get 2.32 times 10 to the negative 3. So not quite doubled, okay? 1.6 doubled would be about 3.2, and we only got 2.3. So remember that when we're calculating it, because of that logarithmic scale and how that ratio is set up, doubling the concentration doubling the concentration of a weak acid or weak base will not necessarily double the concentration of H plus or OH minus. Yep. And then let's just go ahead and find the POH on both of those. We can see what that change would be. POH is just the negative log of the H plus, which gives us 2.79 for this one and 2.63 for that one. So you can see a very small change in pH value and POH value when we're doubling that concentration. Okay. Now another one, we're going to solve for the KB value. Okay, we got the ammonia. We already wrote that reaction up there. I'll go ahead and write it again for us though, just so we have it. Okay, so we have ammonia, which is NH3, and it's going to react with water to produce its conjugate acid, NH4 plus, and OH minus. We don't care about this. We're given the initial concentration of the NH3. We know some of it will go away, and then we're given the pH value. So what can that pH value tell us? Well, it can tell us that the concentration of OH values. So we learned let's go ahead. We know that the concentration of H plus values, or actually, no, let's do the POH. The pH plus the POH has to add up to 14. A lot of different ways you could have figured this out. So if we have a pH of 11.48, we know the POH is going to be 14 minus 11.48, 2.52. So then if we want the concentration of OH minus, it's going to be equal to 10 to the negative POH. So we got 10 to the negative 2.52, which gives us our OH concentration of 3.0199 times 10 to the negative 3 molar. Okay. So those will be our final concentrations. And we got 0.5 minus that number, which gives us 0.497. So a very small change in that concentration. So calculating the Kb value then, okay, we will have that 3.02 times 10 to the negative 3 twice. So I'm just going to put squared there over 0.497, which gives us a Kb value of 1.835, so 1.84 times 10 to the negative 5. Which makes sense because in the previous problem, we were given the Kb value, and it was 1.8 times 10 to the negative 5. So we know we're good there. Okay, cool? Okay, cool. Okay. We looked at the Ka and Kb values for ammonia and ammonium. I want to look a little bit deeper at those. So we have the Kb expression that we were just looking at for ammonia, which is NH3. I'm going to go ahead and represent it with the water, okay, which produces that NH4 plus and the OH minus, okay? And that is our Kb value, which is going to be the concentration of NH4. Oh, that's not where the 4 goes. NH4 plus times OH minus over the concentration of NH3. Now, if we look at the Ka expression for the conjugate acid of ammonia, then we're looking at the ammonium. So we got that NH4 plus that could react with water and form NH3 and the H3O plus. And that has a Ka expression of the NH3 times the H3O plus over the NH4 plus. Okay. Now, I want us to go back and think about Hess's law. Okay. If we were adding up these reactions and looking at the overall reaction, okay, the NH3 here would cancel out with the NH3 here. The NH4 here would cancel out with the NH4 here. So our general reaction would be 2 H2O going to OH minus and H3O plus. Or written even more simply, okay, divided by 2, we got H2O going to OH minus and H plus. Now, when we add reactions, what do we do to the equilibrium expressions? We multiply them, okay? So this K value would be these multiplied together. Now, if you're picturing these multiplied together, again, that NH3 would cancel and the NH4 would cancel, and we would have the concentration of OH minus times that concentration of H3O plus. Yep, not over anything. So that concentration of OH minus times that concentration of H3O plus, or written even more simply, the H plus. And does that look familiar? Yeah, that is the Kw. Okay, that is just the equation for the dissociation of water. And that is on your equation sheets as the Kw equals Ka times Kb. And that will always equal 1 times 10 to the negative 14 at 25. Oops. At 25 degrees Celsius. Okay. Now, this also then means that the Kw expression is equal to the concentration of H plus times the concentration of OH minus, okay, which is also then equal to 1 times 10 to the negative 14. So super useful equation that can help us convert between all of these things. Okay. So if we know the Kb value, then we can find the Ka value. So the Kw equals Ka times Kb. So then if we're solving for the Ka, it'll just be Kw, which is 1 times 10 to the negative 14 over that Kb expression, which we already found as 1.8, or found and was given as 1.8 times 10 to the negative 5, which when you plug that into your calculator, you get 5.56, 5.5555, so 5.56 times 10 to the negative 10. Okay, and that would be the Ka for ammonium, the NH4 plus ion. Okay, cool. So one last skill that we'll talk about is how we can determine if a salt solution is acidic, basic, or neutral. So basically, you're thinking about water. Okay, we got water, H2O, which you can also think of as just an H plus bonded to an OH minus. So if we're thinking about something like NaCl, Na is positive. So it would bond with that OH minus and create NaOH, where the Cl minus would bond with the H plus and make HCl. Now, since HCl is a strong acid and NaOH is a strong base, okay, basically neither of them are going to win. NaCl is a neutral salt, okay? When you add it to water, it doesn't make it more acidic or more basic because it just stays completely disassociated. Neither of them is going to react with water and bond to create that strong acid or strong base because they're going to be completely disassociated. Where if you have something like NaCO3, okay, that Na can create the NaOH, which is a strong base. And then the CO3 can create HCO3, which is a weak acid, or H2CO3, which is a weak acid. Now, if we have a strong base and a weak acid, okay, well, some of those acid molecules are going to form. None of those strong base molecules are going to form. So, we will have some of that H plus go away, but a lot more of that OH minus. So this is a basic salt. Can kind of think of it as the base winning. Okay, where same NH4Cl. Okay, we got the NH4 plus, which could react with water and form NH3, which is a weak base, where the Cl will create HCl, a strong acid. So more H plus ions are still going to be dissolved in solution. Therefore, this is an acidic salt. Okay. And again, unfortunately, you just have to memorize the 6 strong acids and 6 strong bases. Okay. So let's go ahead and do some practice with this. Okay. We do those examples. We look at them. We have barium hydroxide, BaOH2. That is a strong base. So this is a basic salt. Okay. This one would be a weak acid. NH4, okay, produces NH3, which is a weak base, where Cl would produce HCl, a strong acid. This is an acidic salt. Okay. I don't recognize that one, but I know that it could accept an H and be NH4 plus. So I'm going to go ahead and say that that is a weak base. And HBr is on our list of strong acids. So this is also an acidic salt. Where if we have the K, we will have KOH, which is a strong base, and nitric acid, HNO3, which is a strong acid. So this one is a neutral salt. And that's it for weak acids and bases. Okay, cool. Okay, cool.